Hi, this video will cover section 7.2, two-variable linear system. So we will be using the method of elimination to solve systems of linear equations in two variables. So just like our previous section, we will be having two variables only. And then our section after is going to include three variables. 7.3, it will be in three variables. So method of elimination to solve linear equations in two variables, and then we will interpret graphically the number of solutions of systems of linear equations in two variables, and then also use systems of linear equations in two variables to model and solve real-life problems. So in the previous section, if you recalled, we were working mostly with the method of substitution, and with that, we were able to solve systems that were linear, but we also worked with logarithmic and quadratic equations. So right here, we're only going to be working with linear equations. So the method of elimination is also known as addition, because the purpose of this method is to add the two equations with the hope that you can cancel or eliminate one of the variables. So you add to eliminate. And so what we do is we try to look for coefficients that are opposites of each other, like for example here 3x and negative 3x. So if that is the case, then we know that if we add them, we will get 0x. And so because of that, we could say that they cancel out or they get eliminated. So now once you have just one variable and one equation, you could solve for it by just dividing by 3, and so you will get that y is equal to 2. And then after that, you use the back substitution idea, in which you can take any of the equations. For example, here if I take 3x plus 5y, and instead of y I will substitute it with the numerical value that I found, and then that is how I will find the value for x. Just finish solving this one, and we will have 7 minus 10, so that will give me negative 3, and then finally we divide by negative 3 divided by 3, so we get x is equal to negative 1. And so here we have the solution of the system, which will be the order pair negative 1 comma 2. So that is the elimination method. Now whenever that is not possible, that you don't have coefficients that are opposites, like in the case of 3x and negative 3x, then you might have to, you will have to multiply all the terms in one equation, or sometimes in both, by a constant. Now, the way we will choose those constants is going to be dictated by the coefficients that we're trying to get, so that we could get that positive and negative or opposite coefficients. So I will be teaching you how to do that in the examples. So that would be the first step. Now, once you have achieved that, the opposite coefficients, like we had 3x and minus 3x, once you have something like that, you can move on to step 2, which is you add the equations like we did to eliminate one variable. So we did that over here. We got 0x, and then we were able to just have 3y equals 6. So we eliminated one variable, and then from there you solve the equation like we did here. So we got y equals to 2, so you solve the equation, and then from there you use back substitution, just like we did to find the value of x. So we substituted the y equals 2, and then with that we solved for x, and we found that it was negative 1. So and solve for the other variable. And then of course you check if the solution satisfies each of the equations. You could also graph them, see if that is the intersection point. So yeah, do that. Check your solution, especially if you're taking a test. Okay, so for example 2, we have two linear equations, and as you can see, we don't have opposite coefficients. However, we have a negative and a positive. So what I can do very quick is multiply um, the first equation, and in fact, I'm gonna just do it on the next step. So I do like to number them, and I insist on this because for the next section, 7.3, we're gonna be dealing with 3 equations, 3 variables. So it's kind of good to keep track of your equations by numbering them. So if I take equation 1 just like it was, I'm not gonna do anything to it. 2x minus 4y equals -7. And then for equation number 2, I am actually going to multiply it by a constant. And what I'm trying to get, if you notice, we already have negative and positive y's. So if I just multiply by a +4, my second equation, I will be able to get, once I get to this part right here, I will be able to get +4y. That will be canceled with -4y. So the step after this will become that to distribute that 4. So we have to make sure that we multiply it to every single term inside the parenthesis, including the constant term. The one after the equal sign is very important that you do not forget to do that. It's a very common mistake. So you have to distribute that number across the whole equation, everything. So 4 times 5x is going to be 20x. 4 times y is going to be +4y. And then 4 times -1 is going to be -4. So you notice how I got this -4, so please don't forget to distribute that number. So now I'm going to go ahead and proceed with the next step, which is to add equation 1 to equation 2. And so we have 2x plus 20x is 22x. We have -4y plus 4y, and that is going to cancel out. They're opposites. And then we have -7 minus 4, which is -11. Now from here, we're going to solve for x, so it's going to be -11 divided by 22. And we could obviously reduce the fraction if we divide by 11, both top and bottom. So we're going to get -11 divided by 11, we get -1. And 22 divided by 11, we get a 2. So that is our first solution. And now what we're going to do is back substitute. And the easiest thing is to choose the equation. You can use either or, but if you notice here, we have y and it has the coefficient of 1. So we could take equation number 2. I'm going to just rewrite it. So 5x plus y is equal to -1. And so it is easier to choose that one because then we don't need to divide at the end. So here I'm going to substitute the value that I found for x, that is -1/2. And then we're going to have plus y equals to -1. So we can multiply here the 5 times -1/2, and that will be -5/2. So from here, we're going to leave the y where it is, and the -1 also where it is, and we're going to take this fraction, -5/2, to the other side, so it will be +5/2. And we know that -1 in terms of halves is -2/2. So we have -2/2 plus 5/2, and this is going to equal to +3/2, and that will be the value for y. So our solution as an order pair is going to have the coordinates -1/2 for x and then +3/2 for y. So when you're doing your homework, make sure you do read how they want you to enter the answer. They might want you to enter the equation like y equals and then the number, or they might just want the number. So make sure you do pay attention to that. Okay, so the reason that this method works is because when we are multiplying the second equation by 4, as long as we distribute it to every single term, including the constant term, we are creating equivalent equations. So we could say that these two that are highlighted in yellow are equivalent. And that's why the method works. So here again, 5x plus y equals -1 and 20x plus 4y equals -4. They're equivalent, and so therefore the first equation is exactly the same, so we call them equivalent systems. And that is because they will have the exact same solution set, even though we don't have the same coefficients. If we solve for them, they will have the same set. So the method of elimination, the operations that can be performed on a system of linear equations to produce an equivalent system are interchanging any two equations. We're not going to see that yet, but we will see that, or maybe, I guess, in the next section for sure. Then multiplying an equation by a non-zero constant, that's important because it could be positive or it could be negative, but it cannot be zero, the constant, because then you will just get zeros for every term. And then also adding a multiple of one equation of one equation to any other equation in the system. So we're going to see more of that in chapter 8, but I guess this is a very nice introduction. So in chapter 8, we're going to cover these things called matrices, and they are arrays of numbers. And so we're going to see the connection between systems of equations to matrices and vice versa, of course. But this is a very important part of that. We call that elementary row operations. So this slide is trying to just show you that it's also true for systems of equations, not only when we get to matrices. Okay, so interpreting solutions. So we have systems that have exactly one solution. And so the way they look is, especially if we're talking about lines, two lines intersecting at one point. That is how they will look. So an example of that will be like the system here. It has one solution. And then we have systems that could have infinitely many solutions, and that is because the two lines coincide. They overlap, they are identical, they are the same line. They're just written in a different way, but they are the same. So we'll talk about the slopes in a minute. So those lines are identical, so it will be something like here you have one line and then you have the other one overlapping. So those two lines are just the same line, and so they will have infinitely many solutions. Not just any point that you want to think about, but it is reserved to only the points that are on the line. So every single point that fits in this line will be a solution. And so the amount of points in any line is just infinitely many. So we have a third kind that will have no solution, and those lines are parallel. So parallel lines, here we have an example, parallel. So those two lines will not intersect, therefore they will not have a solution. So what we're going to do now is classify them. But before that, I want to finish going over this table. So what happens when you have exactly one solution? You have two lines that have nothing to do, they have nothing in common. So because of that, we say the slopes of the two lines are not equal. That's how you know that you will have only one solution. How would you know if you're going to have infinitely many solutions without solving the system? Well, it is going to be because they have the same slope, but different y-intercept. No, I'm sorry. They're overlapping, so yeah, they have same slope and same y-intercept because they're the exact same line. Then we have the no solution and these lines are parallel. So what happens here is that the slopes are equal, but the difference is that they have different y-intercept. And so that's what happens. So based on that, I'm going to show you a diagram that I use. So please try to write it on your notes. So we have systems of linear equations, and we can classify them into two categories. One will be consistent and the other one will be inconsistent. And consistent means that it has solution or solutions, and inconsistent means that it has no solution. And here we could say that a solution or solutions in plural may, or not may, but do exist. Okay, so based on that, let's talk about the no solution first. And so this one here is going to be the one with parallel lines. And consistent systems, we can divide them into two, and one of them, one of those categories will be called dependent and the other one will be called independent. Okay, so dependent is going to have infinitely many solutions because we have two lines that are overlapping, right? We could say they're like coinciding lines. And for independent, we are going to have only one solution. And that is because you have two lines that have not the same slope, and the y-intercept doesn't really matter if it was the same. Well, if they have the same y-intercept, that will be the solution actually. Okay, so based on those words, consistent, inconsistent, dependent, independent, we're going to be classifying the systems that we have here on the left side on the slide. So let's see. If we look at the images, that's pretty easy because I already went over that. So we have the letter I is, or 1, I guess, is going to be, oh, actually we have to say, if we have to match them. So let's label them first. So the words that we will be using will be consistent or inconsistent. So do they have solutions? The first one, yes. So it is consistent. The third one is also consistent. The one in the middle is going to be inconsistent. It has no solution. And I'm going to add to this that I'm going to add that for the first one is also considered to be dependent. And the third one is considered to be independent. Like that. So now we need to match them. So let's see. So what we're going to be checking for is the slope. So one thing we can do to check the slopes is to solve for y. And as you can see here, the graphs, not the graphs, the equations are written in general form. No, standard form. And so we cannot just look at it and say, oh, the slope is 2, because it's not the coefficient of x. So what I did here is I had to solve for y, so that now it is in slope-intercept form. So as you can see here, it says y equals, so then 2/3 is the slope for that one. And if you're not very good at solving for y, then I'm going to give you a little formula that you could use. And if you take the coefficients, so we know this is a, the coefficient of the x, and this is b. So I'm going to say a is equal to 2 and b is equal to -3. So the formula I'm going to give you is negative a divided by b. So if we use that, we have negative from the formula, and then the value for a is 2. And then the value for b is -3. So if we enter that here, we get the same slope, 2/3. So this will be a pretty good formula to have handy. That's the quickest way to check the slopes. So I'm going to do that with the equation here. And so if I say negative a over b for the slope, it will be negative, and then a is negative itself, so I'm going to have -4 in parentheses, and then we divide that by 6. So this is going to give us +4 over 6, which if we reduce it is going to give us 2/3. So what you could see is that the two lines, line 1 and line 2, have the exact same slope, which is 2/3. So what happens when you have the same slope? Well, we have two options. Either they're the same line or they're parallel. So for them to be the same line, they will have to have the same y-intercept as well. So I guess I'm going to just solve for y on that one as well, so you can see what it will be. So if we take, if we take -4x plus 6y equals -6, and we solve for y, it will be 6y is equal to +4x minus 6. So then y will be equal to +4x minus 6, everything divided by 6. And so this will be y equals to 4x over 6, and then -6 over 6. So if we reduce our fractions, we will get that 4 divided by 6 simplifies to 2/3. And then 6 divided by 6 is a 1. So as you could see here, we have not only the same slopes, but we also have the same y-intercept. So what that means is that we have the exact same line, they're just written in a different way. And so what do we say when we have the same line? So that will be C, the system that comes from part C. It goes here with the coinciding lines, the ones that are overlapping. Okay, there's another way to find the y-intercept, which will be by making x equal to 0. You know that, so let's try that for the next system. So let's go to the first one. And so first I'm going to get the slopes. So here, remember, is the slope. The first slope is going to be negative a over b from equation 1. And that's going to equal to negative 2 over negative 3. And that will be equal to positive 2/3. Okay, now let's take the second slope. The second slope, so for line 2, it's going to be same thing, negative a over b, so it's going to be negative 4 over 6. So that will be positive 4 over 6, and that, you know already, is 2/3. So we have the same slope. And here I'm just going to use the process of elimination because I know that they cannot repeat. So then, since I already have consistent dependent taken, I'm going to go ahead and take inconsistent. So this will be A. And just to prove, we could find the y-intercept of one of them. And so that will be making x equal to 0. That's how we find the y-intercepts. So if we do that, it's like the x that disappears, right? Because it's equal to 0. So then we have that one equation, and to solve for y, it will be 3 divided by negative 3, which is negative 1. So this means that the y-intercept is going to be the point 0, comma, negative 1. And you could see that one here. Now the y-intercept of the other one, it will be, if we make this x equal to 0, it will be negative 4 times 0, so it will be 0. So then we just have here 6y equals 6. And so 6y equals 6. If we divide, I'm going to write it here actually. 6y equals 6. So then y is equal to 6 over 6, which is equal to positive 1. So you can see that the y-intercept of that one will be at 0, comma, positive 1. And that is here. So there you have your two parallel lines, same slope, different y-intercept. And so finally, the one that we have last will be B, and that one will go here. I will just check the slopes. So if I take the slope of the first one, it's going to be negative a over b, so it's negative 2 over negative 3, and that gives me positive 2/3. Now for my second slope, it's going to be negative a over b, so a happens to be a 1, so negative 1 over 2. And there you have it. We have different slopes, so there's nothing else for us to check. We know for sure that that system will have one solution. Okay, so applications. At this point, you may be asking the question, how can I tell whether I can solve an application problem using system of linear equations? So the answer comes from the following considerations. One is, does the problem involve more than one unknown quantity? So more than one. And of course, in real life, we not only have two variables, but there are several examples that we could do with two variables. And if that's the case, if you have more than one unknown variable or quantity, then are there two or more equations or conditions to be satisfied? So if you're looking for one variable, one unknown variable, you only need one equation. If you're looking for two unknown variables, you need two equations, at least. You could have three, but the third one is kind of like pointless. And if you are looking for three unknown variables, you need to have at least three equations. Yes. And I say at least because you could have more, but at least 3. If you have 3 unknown variables and only 2 equations, then there's no way you can solve them. I mean, you can solve them, but only in terms of the others, not with a numerical value for the answer. So the application that we have here, and this is our last problem. So we have an airplane flying into headwind travels the 2,000-mile flying distance between Chicopee, Massachusetts, and Salt Lake City, Utah, in 4 hours and 24 minutes. On the return flight, the airplane travels this distance in 4 hours. Find the airspeed of the plane and the speed of the wind, assuming that both remain constant. So here are 2 unknown variables. Will be one of them is r sub 1, and that is the speed of the plane. So we don't have x and y. We can have any other letter, and we can have the same letter with a different subscript. Then r sub 2 is the speed of the wind. And those are our 2 unknowns. Usually the question is the one that will tell you what your variables should be. The question that says here, find the airspeed of the plane and the speed of the wind. So that's why we label our variables like that. So when it says headwind, it means that the airplane was traveling against the wind. Yes, and for that reason, the air was creating some sort of like um, almost like friction, but of course in the air, because it was a force, and you could see it here. It was a force acting against the speed of the plane. So for that reason, when a plane travels that way, it will take longer than if it was flying in the same direction as the wind. So we get from that statement against the wind, we get the equation R1 minus R sub 2, or R sub 1 minus R sub 2. You subtract the 2 forces. Then with the return flight, that was the same direction, and so it was with the wind. And for that reason, the 2 speeds act with each other, and I guess you get like a little extra speed there. So if it was going faster on the way back, it only makes sense that the time is less. So the original flight going to the destination was slower. So then it makes sense that it will take more time if you're going slower. And for the return flight, it took less time. So you could see the times are listed here in the question. So it says that on the way there, it took 4 hours and 24 minutes. So 4 hours and 24 minutes. And on the return flight, the time was only 4 hours. So 4 hours. So if you notice, the difference was 24 minutes. So what we're going to do is find what were our 2 speeds. R1, so that is our question. What was the speed of the plane, and what was the speed of the wind? And this is assuming that the pilot kept the same speed in both flights. So there is a formula So there's a formula for speed that if you drive, you know this very good. It is the distance. If you look at your speedometer, you could see something like miles per hour, or you may see kilometers per hour. So the formula for speed is distance divided by time. Now, another way for us to refer to speed, we could call it rate, but it will be the same thing, distance over time. So if we want to find what do we have from the problem? We know the distance because it's the same in both directions is 2,000, and it does say in the problem that it was 2,000. We could see it here, 2,000 mile flying. So we know the speed. I'm sorry, we know the distance, and we also know the time. No, we don't know the time. Do we know the time? Yes, we do. Of course we do know the time. But we do not know the rates. Yeah, that's what we don't know. We don't know. That's the question, right? We don't know what the speeds are for the speed of the plane and the speed of the wind. So because of that, and we have some variables, we are going to use a variation of this formula here, and we're going to set it up so that we have rate here, and then we're going to take time out of there because we don't want to have a fraction. We just want to have a linear equation where that looks similar to the ones we've been using. So we take time here, and then what we have left is distance. So even if I do this like with letters, if I have r equals d over t, and I want to solve for d, it will be RT. Okay, so I do that because I have the distance, which is 2,000. That's the same for both. And we have the rates or the speeds. So here's against the wind. So for rate against the wind, and then here I have with the wind. So for rate. And what we need is the time. And so the time is going to be with the wind, it was 4 hours only, and without against the wind or headwind, it was 4 hours plus 24 minutes. Now 24 minutes, we cannot use 4.24 because time is not the units of time are not base 10, so we cannot do that. So we have to use the fraction 24 over 60 because 24 minutes is a fraction that equals 24 out of 60 because there's 60 minutes in 1 hour. So that's why we say 4 plus 24 over 60. So now what we're going to do from here is we're going to rewrite the system so we can work with it. So we have first I'm going to well, I'll just leave it like that. We have 2,000 here. And what I'm going to do is add the two numbers, so the 4 plus the minutes. So 4 in terms of 60 divided by 60, it will be like 4 times 60. So it will be 240 over 60, right? So if you divide this on the calculator, you will get 4. Or you can think of, what do I need to do to the 4 over 1? What do I need to do to the 1 so it has a 60 for the denominator? And the answer is multiply by 60. Remember, you do that top and bottom. So now that we have that, if we want to add the 24 over 60 to this one, is going to give us 264 over 60. And of course, we could reduce the fraction. We could 264 over 60. And so we could divide by 2. We could divide by 4. Yes, we could divide by 4. So let's do that. If I divide, well, let's just divide by 2. So 264 divided by 2 will be 132. 60 divided by 2 is 30. And you see we could divide again. So 132 divided by 2 is 66, and then 30 divided by 2 is 15. Now at this point we cannot divide by 2 anymore, but we could divide by 3. So 66 divided by 3 is going to be 22, and 15 divided by 3 is 5. So those two fractions are equivalent, so that's what I'm going to be using. So 22, it's always better to have a fraction in reduced form. So we're going to use 22 over 5. And then for the second equation, we don't really need much to do. It's just simply that. We leave the 4, and then on the next step, we're going to be distributing that constant to r sub 1 and r sub 2. So let's do that here on the next slide. So we're going to have 2,000. And then if I multiply r sub 1 times the fraction, I will get 22 over 5 r sub 1. Then if I multiply that fraction times negative r sub 2, we will get negative 22 fifths times r sub 2. Okay, and then for our second equation, we're going to have 2,000 on the right side. On the left side. And then we distribute the 4, so 4 times r sub 1. And then 4 times r sub 2. And then from here, we will be solving the system. So since we are in a section that it requires, not requires, but the topic is the method of elimination. So I'm going to do that. And this is, I feel like this is a great example to do that because we have very random numbers there. So what I'm going to do is take the coefficient. I'm going to try to eliminate R2 because it already has a minus and a plus. So I'm going to take the coefficient of the first equation and I'm going to multiply this equation by it. 22 over 5. And then I'm going to do the same with this one. I'm going to take the 4 and I'm going to multiply the first equation by 4. And so I'm going to go ahead and distribute the 4. So 4 times 2,000 is going to equal to 8,000. And then 4 times 22 over 5, that's going to be 4 times 22. So it's going to be 88 fifths r sub 1. And then 4 times negative 22 over 5 is going to be negative 88 fifths of r sub 2. Now we are going to do the same with the second equation, distribute the constant. So 22 fifths times 2,000, we multiply 22 times 2,000. That gives us 44,000, and we can divide by 5 and we will get 8,800 from this product. So it was 22 times 2,000 divided by 5. And then if we repeat that with the terms that have a variable, we will get 88/5 of r sub 1 plus 88/5 of r sub 2. So you could see now that we do have those opposite coefficients. We have negative 88/5 and we have positive 88/5. So that was a purpose so that we could eliminate one of the variables. And that's what I'm going to do next. And so now we add here, and we're going to have 16,800 is equal, and now we have to add this 2 here. So what I'm going to do is add, they have the same denominator, so 88 plus 88 is equal to 176, and then they're both fifths, so over 5 r sub 1. So we only added the numerators. And from here, I'm about to solve for r sub 1. So one very quick way to solve for r sub 1, if you notice, the 5 is dividing to r sub 1 because that is equivalent to having this expression. So if we have here 16,800 and we take the 5 across, from dividing is going to be multiplying, so I'm going to put it up here. And the 176 here is multiplying to the r sub 1, you can see that. So if we take that across, it will be dividing. And you could see how the fraction that we're using here in the original coefficient of r sub 1, they are inverses of each other, or sorry, not inverses, reciprocals. So what I'm going to do now is multiply the two fractions here. Well, the fraction times the 16,800, so it's going to be 16,800 times 5, and then I am going to divide by 176. And so that gives me 477.27, and that is equal to r sub 1. Now, to find r sub 2, we could take one of the original equations. I will probably take this one here. It's the easiest, or we could take this variation right here. So it will be 2,000 equals to 4 r sub 1 plus 4 r sub 2. And now that we know the value for r sub 1, 477.27, we are going to substitute that one here. Remember, that is the speed of the plane. So we get 2,000 here. We get 4 times 477.27. And then we still have the plus 4 r sub 2, and remember that is what we're actually going to be solving for. So I'm going to multiply that times 4, and I get 2,000 here, and we're going to get here 1,909.09 plus 4 r sub 2, and remember that's the variable that we got to solve for. So this is going to be 2,000 minus 1,909.09, and that is equal to 4r sub 2. So I'm going to subtract that. 2,000 minus 1,909.09, and I get 90.91, and this is 4r sub 2. And so last thing I have to do is divide by 4 to isolate r sub 2. And so r sub 2 will be 90.91 divided by 4, and that is equal to 22.70. I'm gonna round it to 73 r sub 2. So the speed of the plane, I'm sorry, not the speed of the plane. This is the speed of the wind, 22 miles per hour, 22.73. And the speed of the plane is here, 477 miles, 0.27. So you could see it does kind of make sense. The speed of the plane, it is a lot higher than the speed of the wind. If that was not the case, then the plane would have probably crashed. Okay, so this is the end of the video.